Hello, class. I am coming to you today to look at section 4.4, concavity and the second derivative test. So Calculus 1, section 4.4 is what we're going to look at today. So up until this point, let me focus on last section. 4.3, we were focused on using the first derivative test. And the first derivative test determined for us what our original function was doing in terms of increasing, decreasing, where we have relative extrema, or relative max, or relative mean, things of that nature. The second derivative test, what we're going to look at today, focuses on concavity, where we have basically turning points in the function in the graph, concavity where it turns, where the function turns or is considered concave down or concave up, and then helps us to identify our points of inflection. Sorry. Okay, so I am going to share my screen. We're going to talk about a few things and look at examples. Let me do that. All right. I'm going to zoom in here. So again, we're discussing concavity and the second derivative test in section 4.4. So chapter 4 is relegated to module 3, okay? So just be aware of that, how it kind of changes. It's just the way that the sections are numbered. And then remember, our last module is actually focused on chapter 5, okay? Module 4 is for chapter 5. Module 3 is for chapter 4, okay? So we're looking at concavity and the second derivative test, all right? So let's talk about concavity. You have seen that locating the intervals on which a function f increases or decreases helps to learn more about the graph. So we looked at where a function increases or decreases back in 4.3. In this section, we're going to see how locating the intervals on which f prime, the first derivative, okay, this is f with a little mark here, f prime, increases or decreases can be used to determine whether the graph of the original function f is curving upward or curving downward. Okay, so we'll be looking at the first derivative. We'll be looking at f prime by finding f double prime, by finding the second derivative. So, definition of concavity. Let f be differentiable on an open interval I. The graph of f is concave upward on I when f prime is increasing on the interval. So, it'll be concave up when the first derivative is increasing on some interval. And it'll be concave down when f prime is decreasing on whatever that interval is. Okay? Here's a picture, a graphical interpretation of concavity. So here it says that f be differentiable on the open interval I. If the graph of f is concave upward on I, then the graph of f lies above all of its tangent lines. So concave up means your tangent lines will actually lie below the graph, or in other words, vice versa, the graph of f will lie above all of the tangent lines. Remember, the tangent lines are just where we create a line through some point along the function, okay? And the slope of the tangent line tells us what the slope is at that certain point along the function, okay? So when it's concave up, the function lies above all of the tangent lines. The reverse is true for concavity when it's downward or concave down. If it's concave down, then the function f will lie below all of its tangent lines. Okay? And as you can see, that when you're looking at these tangent lines, the slope of these tangent lines, which is f prime, appears to be decreasing. Okay? The slope is going down, or f prime is decreasing. All right, to find the open intervals on which the graph of a function f is concave upward or concave downward, then we need to find the intervals on which f prime is increasing or decreasing. So what that means is we can find out where the first derivative is increasing or decreasing, and that can tell us what f is doing in reference to concavity, up or down. Okay? For example, the graph of this cubic function, 1/3 x cubed minus x, is concave downward on the open interval negative infinity to 0 because f prime, which is the derivative of f, is decreasing there. Let's take a look at that. So here is your original function, okay? The slope at this particular tangent line, or at this point here, is 0 because that's a critical value. You can see that would be a critical value. So the slope is 0 there. But if we focus on the interval from negative infinity to 0, we can see that the function is concave down. And if we draw tangent lines, all of our tangent lines along this part of the graph lie above the actual function. Okay, so it is concave downward, which means your derivative is actually decreasing here. Okay, and you can see that is happening when you actually look at the graph of the derivative. So from negative infinity to 0, the derivative is decreasing, going down. Okay? And it actually is continuing to decrease even here from negative 1 to 0. But then it turns to increasing here. Okay? So the concavity of f is related to the slope of the derivative. It's related to the slope of the derivative. All right, so we've got some tests for concavity, which we're going to look at. Some examples here in just a little bit. The following theorem shows how to use the second derivative of a function f to determine intervals on which the graph of f is concave upward or concave downward. And of course, it tells us something about the function, and we can look even further at the function by examining its actual graph. But it is important that you understand that the derivative alone can reveal some things to you about the original function, even if you can't look at the original function's graph. You can still learn some things about the original function. Even if you can't look at the graph of it, you can examine the derivative. You can examine the second derivative to learn things about it. Okay? All right, so this theorem, test for concavity, says let f be a function whose second derivative exists on an open interval I. If f double prime, if the second derivative is positive or greater than 0 for all x in that interval, then the graph of f will be concave upward on that interval. So if the second derivative is positive for that interval, for that given interval, then the actual function will be concave upward on that interval. If the second derivative is negative for all values of x on that interval or on some interval, then the graph of the original function f will be concave downward on that interval. Okay? So in order to apply this theorem, we do have to locate our critical values in a way, if you think about it. We're not necessarily going to call them critical values, I guess, but yeah, they can be called critical values because they're the critical values of the second derivative. But it is, normally we call the critical values only for the first derivative. But to apply 4.7, this theorem, we do still have to think about the second derivative and where it's equal to 0 and also where it does not exist. And we will use those x values to determine test intervals. Okay, so we do have to break up the number line, remember, into our intervals the same way or similarly to how we use the first derivative test. So let's look at this first example here. It says determine the open intervals on which the graph of f of x, which is e to the negative x squared over 2, is concave upward or concave downward. So first off, we want to understand or observe that this is just a natural e function, which is continuous on the entire real number line. Okay, the entire real number line. If you wanted to look at that, you can examine the graph of it to get a better understanding or to just verify that. So y equals, I'll put the f of x function in y equals. So e, I have to press the second key and then the LN key for the e. Okay, e raised to the, that little rooftop there, raised to the negative x squared over 2. And I'm going to close that off. That's my whole exponent. Okay? And I'm just going to look at the graph of that. Hopefully I can get a decent picture. I'm going to have to zoom out. I definitely have to zoom out. So let's go zoom and let's go standard. So just zoom standard. And that's an okay graph. I could have even maybe adjusted the window, maybe not did the 10 by 10 standard, but instead maybe adjust my y. I don't have to have negative 10 on y min. And the reason is because it's not anywhere down there. The graph is not anywhere in the negative y. It's mainly up here in the top 2 quadrants. So I'm going to adjust my window. I'm going to make my y min just be like maybe negative 2. And my y max, let's make that 5. And then let's hit graph. And we can see a little better picture. There we go. So it is definitely continuous on the whole number line. There's no breaks in the graph. There's no gaps or anything like that. Okay? So the first thing we're going to do, after we verify that it is continuous on the number line, the first thing we're going to do is find the first derivative because we got to get the second derivative. So I'm going to say find first and second derivative. I'm only needing the first one just so that I can get the second. Okay? So let's get f prime first. Okay? Now this is technically a chain rule problem because you got a function within a function. Notice in the exponent you've got the negative x squared over 2. So we do have to consider that. Okay, we got to take the outer derivative and then the times the inside derivative. Okay. So the derivative of e to the x power is just e to the x power. So the outer derivative is just going to be itself, e to the negative x squared over 2. Then we say times the derivative of the inside, which would be the derivative of the exponent. That's going to come down as a negative 2. Actually, it'll come down as a negative 2x, and then we already have this 1/2 here, so I'm going to write it like this. Or 1/2, because it's negative x squared over 2, so I'm going to pull the 1/2 out front, and I'm going to bring down the 2, and then I've got the x. Okay, so that actually ends up becoming the 2 and the 1/2 cancel. So that actually ends up becoming a negative x e to the negative x squared over 2. So that's f prime. Now we're going to find f double prime. Okay, so f double prime, I have to take the derivative of this. And this now is a product. this is the product of two functions. We got the negative x and we got the e to the negative x squared over 2. So I'm going to have to use the product rule, and within the product rule, I'll apply the chain rule for this part. All right, so according to the product rule, it's first times the derivative of the second. So first, negative x squared times the derivative of the second, which will be e to the negative x squared over 2 times negative 1/2 2x. So that's first times the derivative of the second plus the second, e to the negative x squared over 2 times the derivative of the first, which would be negative 1. Okay, the derivative of negative x is just negative 1. So we'll clean this up, of course. So right now, this is all a product, okay? So the 2 and the 1/2 cancel out. The negative and the negative are also going to cancel out because you got a negative x, but then look right here, you still got that negative x. So technically, you've got a, let's write that as x squared, and then we've got e to the negative x squared over 2, okay? Then I've got minus e to the negative x squared over 2. So that's what I have currently, okay? Now, I am going to make this look a little nicer. I can pull out this factor of e to the negative x squared. I can pull that out. E to the negative x squared over 2. I'm going to factor that out, and that'll leave me with x squared minus 1. Now I'm going to leave that as my derivative, my second derivative. I've got my second derivative now, okay? Now, we have to ask ourselves, where is f double prime equal to 0 and or f double prime does not exist? That is the question, okay? I will say that it exists everywhere, so we won't have to worry about that, but we do have to find where it equals 0, okay? Also, let me say this. Sometimes you might get a function, an original function, who is actually not continuous everywhere. So in addition to these values, setting up your intervals, your test intervals, you would also have to include any value that f of x might not be continuous at also to use as your intervals. Because you cannot say that the function would be graphed over, or what the function is doing over an interval if it's not actually defined over some interval. But this one actually is continuous everywhere, so we don't have to worry about it. But what I'm getting at is, if ever there are x values at which your original function is not continuous, then those values should also be used along with these values to use to set up your test intervals, okay? And I think I've got that at the bottom of my notes on the other page too. All right, so let's find when e to the negative x squared over 2 times x squared minus 1 equals 0. Let's find that, okay? So you technically have a product here, e to the negative x squared over 2. We can place that equal to 0. And x squared minus 1 equal to 0. Okay? Technically, this is never equal to 0. Even if you were to put 0 in the exponent, this would still be 1. So you're going to have to toss that out, or basically kind of divide out by it on both sides. I could have done that. I could have just divided out by e negative x squared over 2 on both sides, and it would have canceled out anyway, okay? But it's canceling out. Now, this is what we're going to be looking at. X squared minus 1 equals 0. We're going to solve that using the square root property. Take 1 over to the other side. So now I've got x squared equals 1. And then I'm going to take the square root, plus or minus square root of 1. So x is just plus or minus 1. Okay? So those are our values where f double prime was equal to 0. So now we're going to use those values to set up our interval, okay? Now keep in mind our interval, our original function rather, is going from infinity or negative infinity to positive infinity. Our original function is continuous everywhere. So when we set up our intervals, we're breaking up the number line from negative infinity to positive infinity. So I'm going to draw a line here like I did in class from negative infinity to positive infinity, and I'm going to place my quote-unquote critical values of f double prime, or values of f double prime when f double prime is equal to 0. We're going to place those on the number line. So negative infinity to negative 1, negative 1 to positive 1, and then infinity, positive infinity. So here will be your intervals, negative infinity to negative 1, negative 1 to positive 1, and then 1 to infinity. Okay? And then, of course, I like to use a test value. Okay? And remember, we're going to look and see what that test value is doing to f double prime, or how it acts, whether it makes f double prime positive or negative. So we're going to pick a test value within each of those intervals, and we're going to look at the sign of f double prime, and then that will help us to determine what f is actually doing. Conclusion is f, the original function, concave, I cannot spell that, concave, up or down? That is the question. I just put that little question there so that you'll know what kind of conclusion you're trying to draw. And we're talking about concavity when we're looking at the second derivative. So my test values, I'm going to roll with a -2. Okay, as long as it's in that interval. I'm going to roll with 0 here, right in the middle of -1 and 1. And I'm going to roll with +2. And I like to do that because most times these two numbers act similarly. Okay, when you have the same number. Most times, not always, but most times. So let's see what f double prime is. So f double prime at -2, basically, I will be plugging in -2 wherever I see x here, and I should get a positive. Okay, let's look at that. So e to the -2, actually, the sign is negative already, and then I've got -2 squared over 2. I'm going to close that off. And then I'm going to say -2 squared. Actually, I might need to include another parentheses, or just go ahead and put 4 there, and then -1. And I got a positive. Not decimal, but we're more so concerned with the sign. It is greater than 0. It is positive. Okay? And if you think about it, the only thing that's different between -2 and +2 is that sign. But when I plug in the -2, it turns into a positive anyway there. And likewise here. So I should also get a positive answer when I plug in +2. So what I'm going to do is recall this. I'm going to go in and delete where I have that negative. Now the original function had a negative in it, but then I plugged in a -2. So that first negative I keep. That negative I keep. That one is the one I'm deleting. And I press enter, and I got the exact same answer. Okay? So f double prime at +2 is also positive. And I suspect that x at 0, the function f double prime evaluated at 0, I suspect will give me a negative. So let's take a look at that. So again, I'm going to recall this, and I'm going to go in wherever I see 2, and I'm going to place it with 0. It's a bit easier than trying to plug calculator lets me recall, so I'm going to recall. And I got a negative. So f double prime at 0 is less than 0, so that is negative. So when f double prime is positive, the original function is concave upward. Okay? So what that means is also, you can even go further, if the second derivative is positive, that means the first derivative will be increasing over this interval. Hence, the original function is concave up. Here, the second derivative is negative, so it means the first derivative is decreasing over the interval, so the original function is concave down. And then lastly, the second derivative is positive here, so it is concave up again. Okay, there you have it. We just used the second derivative test. Not too bad. And like I said, if ever you have values of the original function that make the original function not continuous, or there are certain values where the original function isn't continuous, those values have to also be used to set up your intervals. So it would be, in addition to -1 and +1, it would be some other number if our function was not continuous everywhere. Okay? All right, let's see what else we have here. I think I'm going to look at my second example, and then we'll go and look at some homework problems. The homework problems aren't terrible. I think my second example is more complex than this. Actually, my second example is very much like number 6. Yep. So I might just do number 6 from the homework. Yeah, my second example in my notes is x squared plus 1, or sorry, yeah, my example in my notes is x squared plus 1 over x squared minus 4. Well, in the homework, it's x squared plus 6 over x squared minus 4. So it's very, very similar, almost the same kind of problem. So what we're going to do then, instead of doing this example, I am going to maybe replace that with example number 6 from the homework. And again, this is section 4.4. Okay? So from the homework, it says determine the open intervals on which the graph is concave up or concave down. Determine, and I think it was the exact same, yeah, same direction. Determine the open intervals on which the graph of f of x is concave upward or concave downward. Okay? So your function is x squared plus 6 all over x squared minus 4. Okay? Alright, so the first thing we have to do, of course, is find the first derivative. Okay? The first derivative. Actually, let me say something here too. Even though I suspect no, there actually may not be. Let's look at this one. So we are going to find values where f double prime, where the second derivative is equal to 0, or where it doesn't exist, okay, to help us set up our intervals. But also, remember, if your original function is not continuous anywhere, you have to use those values as well to set up your intervals. So take a look. This is a rational function. It has a denominator. If ever that denominator is 0, then this function is doesn't exist there at those values. So therefore, the function, the overall function, would have breaks or gaps or holes in its graph. So f of x is not continuous. F of x, the original function, make sure you're understanding we're talking about the original function, is not continuous at x equals -2 or +2. And that is because, again, you would get 0 in the denominator. If you square either one of those, -2 or +2, you would get 0 in the denominator. So those values will be used to set up our intervals, to figure out where we have turning points in our graph, or if we have some turning points where we have a change in concavity of our graph. Okay? All right, now let's find f prime. So f prime will be, looks like we're going to have to use the quotient rule. It's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay? I have to use the quotient rule. So it's going to be bottom, x squared minus 4, parentheses, times the derivative of the top, which is 2x, minus the top, which is x squared plus 6, times the derivative of the bottom, which is 2x. Okay? And then I have over x squared minus 4 squared. Okay? We're going to clean this up a little bit. It should kind of clean up nicely. When I use the distributive property here, I'm going to use it and I'll write the final product, the final answer over here. So I'm going to use the distributive property. So this is going to give me 2x cubed minus 8x right there. And then I've got minus here. This is going to give me 2x cubed minus 12x. And the reason I've got minus here is because I'm taking that minus through. So when I write these terms over here, they're both going to come over as minus or as negative. So I've got 2x cubed minus 8x minus 2x cubed minus 12x all over x squared minus 4 all squared. Okay? So the 2x cubed and the minus 2x cubed cancel, and the negative 8 and the negative 12, what does that give me? Negative 20x, negative 20x, and then I've got all over x squared minus 4 squared. Okay? So that is my first derivative. Now let's find the second derivative. So now we have to take the derivative of this. Okay, so we're going to say bottom, which is x squared minus 4 squared, times the derivative of the top, which is negative 20, minus the top, which is negative 20x, times the derivative of the bottom. Okay, now this bottom derivative, I've got to take the outer derivative, where I'm going to bring down the 2, keeping the inside the same, lowering the exponent by 1. Then I say times the derivative of the inside. Okay, so this negative 20x is going to be multiplied to the derivative of the bottom. So the bottom derivative will come down. I'll have 2, and I'll keep the x squared minus 4. And then I'll say times the derivative of the inside. Derivative of x squared minus 4 is just 2x. The 2 comes down, and the 4 just drops off. Okay, and then that's going to all be over my denominator squared. So basically, x squared minus 4 squared, I'm going to square again. So that's just going to be x squared minus 4 to the 4th. Okay, when I square it again, I get to the 4th. Okay, so let's clean this up some more. Let's see what we can do here. You want to always try to clean it up as much as you can before you try to do any solving. This looks nuts. So we definitely want to clean it up. So I'm going to multiply through with 20 here. Actually, I may not do that I'm looking at this now, and it looks like I might be able to do a little bit of manipulation. Let's see. Well, first off, I can't distribute that negative 20 because this is squared. So let me cross that out. Instead of writing this x squared minus 4 squared, let's write x squared minus 4 times x squared minus 4. Okay? And then I still have this times negative 20. All I did was expand that out. Okay? But I couldn't use the distributive property because that had a square. Okay? Now, let's get rid of this minus here. Let's go ahead and say minus a negative is just plus 20x. And then here I've got 4x. So I'm going to say 2x times the 2. So I've got 4x, and then I've got x squared minus 4. Okay? All right. So I've got an x squared minus 4 in both of these terms that I think I'm going to pull out. I think I'm going to factor out, because this is a product. This is all a product here. 20x, 4x, x squared minus 4. I actually could go ahead and multiply these two together. I think I will. And I'll go ahead and let me go ahead. So when you're cleaning this up, you may have to play around with it a little bit, you know. I guess you can say that's what I'm kind of doing. But I'm simplifying. Don't get me wrong. I am definitely simplifying and cleaning it up, okay? But I had to realize that I couldn't use the distributive property there, so I expanded it out. And the only reason I chose to do that is because I saw that I had one of them over here. And I knew I could probably factor one out. Okay, so that's why I expanded it out. Instead of writing it as this binomial squared, I wrote the binomial twice. Okay, so I'm going to put negative 20 out front here. I'm going to write x squared minus 4, x squared minus 4. And then I've got plus 20x. Actually, let's go ahead and say that's 20 times 4. So let's go ahead and say 80x squared. And then I've got x squared minus 4. All over x squared minus 4 to the 4th. Okay? So, all right. I'm going to factor out, I'm going to factor out an x squared minus 4 from here. And the only reason I'm doing that, I'm factoring out from both terms here, and I'm choosing to do that because I've got x squared minus 4 on the bottom too, and it'll cancel out at least with one of those. So I've got negative 20 x squared minus 4, and then I've got plus 80x squared. So I factored out the x squared minus 4, x squared minus 4 to the 4th power on the bottom. So this x squared minus 4 will cancel with one of those that's in the bottom. So on the bottom now, on the top now, I have, and this is remember f double prime. So I have negative 20x squared minus 4. And then I've got plus 80x squared. So I'm going to use the distributive property here. So I've got a negative 20x squared. And then I've got a plus 20 times 4. What is that? 80. A plus 80. And then I've got plus 80x squared. And that's all over x squared minus 4 cubed. Okay? All right. Now, you can do some canceling here and here. Well, you can simplify. I won't say cancel. You can simplify. A negative 20x squared and a positive 80. So you got 60, positive 60x squared. And then you got plus 80 all over x squared minus 4 cubed. Okay? So that is f double prime. Now, what we want to do is see where it's possibly equal to 0. So this is f double prime. Now, where is f double prime equal to 0 or doesn't exist? Well, f double prime doesn't exist at -2 and +2. And we already knew to make sure we include those values because the original function f doesn't exist at those numbers either. So we're definitely using -2 and +2, okay? So -2 and +2. That's +2. That's when it doesn't exist. Now, where is it equal to 0 is the question. So 60x squared plus 80 over x squared minus 4 cubed equals 0. Let's see. Does it equal 0 anywhere? All right. So we've got 60x squared plus 80 over x squared minus 4 cubed equals 0. So the first thing I'm going to do is eliminate x from the denominator. So this denominator here, I'm going to multiply both sides by it. And it's going to just basically get rid of it for me. Because it's canceling there. And I have 60x squared plus 80. And over here I still have 0. Okay? All right, now to solve this, I am going to subtract 80 since it's just a x squared term and a constant. I'm going to take 80 to the other side. I don't have to factor it, in other words. I can solve it using the square root property as long as you've got like some square equal to some number. And I will have it like that once I take 80 over there. So I've got 60x squared equals a -80. I'm going to divide out by 60. So x squared equals what? 4/3, -4/3. Because 2 goes into, or technically 20 goes into both of them. The zeros cancel, and then 8 over 6 reduces to 4 over 3. Okay? Now, x squared equals a -4/3. That is an issue. The reason is because you cannot take the square root of a negative number and get a real number. You cannot take the square root of a negative number and get a positive real number, or get an actual real number. So when we do this, it ends up introducing I, and then we got square root of 4/3. So this is imaginary. Because it is imaginary, f prime has no real solution or f double prime, I should say, for when it's equal to 0. Okay? So because, I'm sorry, let me speed that up a bit. Okay. So because there are no real values for when f double prime equals 0, our intervals are going to be set up using only when it was non-existent, -2 and +2. So our intervals from -infinity to -2, from -2 to +2, and then from +2 to infinity. Okay? We'll choose a test value in that range, or in each interval. We'll look at the sign of f double prime. And then we'll draw an equation for f. And that is where we discuss concavity. Up or down. Okay? right, so test value, let's use -3, let's use 0, and let's use +3. As long as you have a value that lies within each interval, doesn't matter really what you use, but I try to keep it simple, so I'm using these values. Now, when I plug these values in, I'm plugging them into f double prime. And when I plugged in -3 into f double prime, remember f double prime is right here. When I plug in -3, I would plug in -3 there on top, and I would plug it in down here on the bottom. When I plug in -3, I get a positive number. Okay? When I plug in 0 into f double prime, I get a negative number, less than 0. I get something negative. All right, and then when I plug in 3 into double prime, f double prime, I get again a positive number. Okay, so if f double prime is positive over this interval, then that makes the function, the original function, concave up. It's negative here, so that makes the original function concave down. And then it's positive here, so it's concave up again. Okay? And that is the problem. So honestly, the hardest part, the longest part, is using the formulas to get the derivatives. Because you have to recall product rule, quotient rule, and you'll have your, formula sheet with these rules on them, but still, you have to be able to use them. You have to be able to recognize when to use them, whether it be the quotient rule, the product rule, the chain rule. That's the difficult part, okay? And then setting up your intervals, getting a test value, and then plugging that test value into the second derivative so that you can draw a conclusion about the original function. Okay? All right, let's see what else we have. I may try to look at one more example here. Let me see what else we have. A lot of these problems are really similar. Let's look at one more thing from our notes, though, to go a step further with the second derivative and concavity. So, on page 6 of our notes, when you have a change in concavity, that change, the point at which that occurs, which is typically where f double prime is either 0 or non-existent. That is where you have a point of inflection. It's where you have a change in concavity. So these all represent points of inflection. Here you go from concave up to concave down. That's a point of inflection. Here, concave down to concave up. You had a flat tangent line there. Okay, where the slope was 0 there. And in here, concave up to concave down, you have a vertical line at that point, a vertical tangent, which means that the slope doesn't exist there. Okay? All right, so a point of inflection. Let f be a function that is continuous on an open interval, and let c be a point in that interval. If the graph of f has a tangent line at that point, cf at c, then this point is called a point of inflection of the graph when the concavity changes from upward to downward or downward to upward. So basically, when you have those critical values, if at those critical values you have a change in concavity, so basically remember you're setting up your intervals. Your intervals are set up using your critical values, whether the critical values be because the original function wasn't continuous, or if those critical values are found when f double prime equals 0 or f double prime doesn't exist. Those are your critical values. Those values are used to set up your intervals. So once you look at your intervals, if your intervals have a change in concavity, then those critical values become points of inflection. If there's no change, then they're just critical values and not necessarily a point of inflection. Okay? So the definition of point of inflection requires that a tangent line exists at that point of inflection. Okay? Some calculus texts do not require this. For example, after applying the definition above to this function, then technically we would say f does not have a point of inflection at the origin, at 0, even though the concavity of the graph changes from concave downward to concave upward. So to locate possible points of inflection, you can determine the values of x for which f double prime is equal to 0 or f double prime does not exist. And this again is basically kind of what we did before. We're just now going to call them points of inflection. And it's similar to what we did when locating relative extrema, when we were using the first derivative test. Okay? All right, so we'll look at this one in our notes here, example 3 in our notes, and then I think there's something else we'll look at. All right, so a point of inflection. If f at C is a point of inflection of the graph of f, then either f double prime at C equals 0 or f double prime at C does not exist. So in other words, C becomes some critical important value of f double prime. It's either where f double prime is equal to 0 or where f double prime doesn't exist. All right, so on this example, it says determine the points of inflection and discuss the concavity of the graph. So I can look at this one, or I can look at, I'll tell you what, I think I will look at number 7. It's a similar problem. The function itself, I'll cross this function out and look at example from homework. And it's number 7. Okay, it's number 7. So f of x equals x cubed minus 6x squared plus 28x minus 40. Okay? All right, so we're going to find the first derivative, and that is bring down the 3, x squared, bring down the 2, that becomes 12, because it'll multiply with the 6, x, and then this becomes plus 28, because the derivative of 28x is 28, and the derivative of the constant just drops off. Okay? Now we'll take f double prime, and we'll find f double prime. So we'll bring down the 2, 2 times 3, that becomes 6x, and then 12x, that becomes just a minus 12. Okay? So f double prime is continuous everywhere. So find where f double prime equals 0. Okay? So f double prime equals 0, 6x minus 12 equals 0, take 12 over, I just added it, cancels there, we got 6x, and then divide by 6, we got x equals 2. Okay? So f double prime equals 0 and x is 2. That is our only value, our only critical value that we'll use to set up our intervals. The original function was continuous everywhere, so we don't have any values that we would have to eliminate or leave out. The second derivative was continuous everywhere, So the only value we could find is when the second derivative is equal to 0, and that is at 2. So our intervals are negative infinity to 2, and then 2 to positive infinity. Because remember, the number line, negative infinity to positive infinity, you only have one value C, one critical value, and it's 2. So negative infinity to 2, and then 2 to positive infinity. And then we will look at a test value. Test value, and then using that test value, we'll look at the sign of double prime. And then we'll draw a conclusion. Okay? All right. So looking at the test value, how about we use anything really? I'm going from negative infinity to 2. How about we use 0? And then 2 to infinity, let's use 4. Anything will work though. So the sign of f double prime at 0. So f double prime right here. So 6 times 0 minus 12, that is less than 0. That is negative. It gives me a negative 12. So that is negative. Okay? Now that means my original function must be concave down there. Okay? Here, when I plug in 4 times 6 is 24 minus 12, that is positive. It actually gives me 12, it's positive. So that means the function, the original function, is concave upward. Okay? And again, I just crossed out the original example that I had and pulled number 7 from the homework. It was still a polynomial. It's just the one from the homework had more terms. Okay? All right, one more thing I want to talk about here in this section, and it's just taking this and actually calling it what it is, which is the second derivative test. What else it helps us to determine. Not only just concavity, but what else it helps us to determine. You're looking at the second derivative. So, the second derivative test. In addition for testing for concavity, the second derivative can be used to perform a simple test for relative maxima and relative minima. So we could go a step further with the second derivative test, and it can tell us not only about concavity of the original function, it can tell us where the original function may have points of relative extremes, whether it be a max or a min. Okay? So when you have a function that is concave up, where f double prime is positive on some interval, then that means there must be a relative min. So concave up means your horizontal tangent will lie below, or your tangent line. I won't say necessarily that it's got to be horizontal, but your tangent line would lie below the function graph, which means you would have a relative minimum there. If your double prime, if f double prime at C is negative, then that means your tangent line at that point would lie above the function, or in other words, the function would lie below the tangent line, which would give you a relative max. Okay, so concave up, relative min, concave down, relative max. It's the opposite. Up, think minimum, down, think max. And that is the second derivative test. So if not only just concavity, if f double prime is positive at that number C, whatever C is, then you have a relative minimum there. If f double prime is negative, then you have a relative maximum there. Okay? And if f double prime at c is exactly 0, then the test fails. F could still have a relative max, a relative min, or neither. But in this case, you would have to use the first derivative test to determine it. Okay, so sometimes the second derivative test fails, and you may need the first derivative test. Okay? All right, so I am going to, let's see here. Oh, on the previous problem, I did not finish this up. So when you go from concave, because we did find points of inflection here. When you go from concave up and down, when you change that, or vice versa, we're going from concave downward to concave upward, then we do have a point of inflection. So we have a point of inflection. Okay, when it has a change there. So it's going from concave down to concave up. You do have a point of inflection. I wasn't trying to write, but I don't know what that is. Okay, so let's look at this last example here in this section, the second derivative test. And it says, find the relative extrema using the second derivative test. Okay? So what I'm going to do is find the critical values of f double prime. Okay? Because according to the second derivative test, I need f double prime. The first thing I'm going to do is find f, or f prime, first derivative. So that would come down, the 5 would come down, making that a negative 3 times 5 x to the 4 plus, the 3 comes down here, 5 times 3 x squared. So this is negative 15 x to the 4 plus 15 x squared. Okay? All right, then we'll find f double prime. Taking the derivative here, bring down the 4. 4 times negative 15 x to the third plus 2 times 15 x. So 4 times negative 15, I get a negative 60 x to the 4, and I'm sorry, x to the third, because that's the exponent right there. And then I get plus 30x. Okay? Now, find critical numbers of f double prime. All right. Find critical numbers of f double prime. Actually, I am wrong. Find critical numbers of f prime, not double prime. So, according to this, let's go back here. Let f be a function such that f prime at c equals 0. Okay? So you got to find the critical values. The real critical values are found from the first derivative of the first derivative. Then we evaluate f double prime at c, at those values c, to figure out if we have max and min. Okay? So I actually need to take the f prime, which is negative 15 x to the 4 plus 15 x squared, and I need to solve that. So I'm going to pull out, I'm going to pull out 15 for sure, and x squared. How about we go a step further and make that a negative that we pull out? Let's make this a positive leading coefficient. I'm going to pull out a negative 15x squared, and that will leave me with a positive x squared minus 1. Okay? Okay, so I pulled out the negative, so it made that become positive, and it made that plus become negative. Okay, so then I've got negative 15x squared equals 0, and I've got x squared minus 1 equals 0, because you have the whole product place equals 0, then you break the product apart and place the factors equals 0. So here, this would just be 0. When you divide by 15, then you still got 0. Then you take the square root, you still got 0. Okay, so x equals 0 here when you solve that. Over here, you're going to add 1. So x squared equals 1. So x equals plus or minus 1. So your critical values from f prime are 0, negative 1, and positive 1. So now you're going to evaluate f double prime at those values to figure out if you have a relative max, min, or what the case may be. So you're plugging these into the second derivative. Okay? So negative 1 plugged in, you got negative 60 times negative 1 cubed plus 30 times negative 1. Here, negative 60 times 0 cubed plus 30 times 0. And then here, negative 60 times 1 cubed plus 30 times 1. So here you get 30. So you got 60 minus 30, so you're going to get 30, which is positive, which means you have a relative mean there. If it's positive, according to the test, then there's a relative mean here at x equals negative 1. Here, that's just 0. Test fails. And here, this is negative 30, which is less than 0, which is negative. So that means you have a relative max at x equals positive 1. Okay? And there you have it. I'm looking through. All right. Let's shorten some of this homework, cut it down a little bit. But that wraps up 4.4. I will see you soon.